Thank you very much for the invitation to speak here. I would like to talk a little bit about central extensions of the group of exact volume preserving diffeomorphisms. So this group will be a Lie group if the manifold is compact. But a lot of what I'm going to say actually doesn't involve the group, it involves the Lie algebra. So if I'm talking about the Lie algebra, I won't need any compactness assumptions. So in that case, M is just a manifold with a volume form. And a vector field on M is volume preserving if the Lie derivative along this vector field of the volume form is 0. Divergence-free. Equivalently, Lx is ixd plus dix, but d of mu is equal to 0 because mu is a top form. So equivalently, ix of mu is closed. It's exact divergence-free if ix of mu is not just closed but exact. So it's kind of analogous to a vector field which can be symplected, but it can also be Hamiltonian. Ix of omega is not just closed but exact. If it has a volume form, it's volume forms.
Could be a density, and exact is not so easy.
Orientable manifold. So X is exact divergence-free if Ix of mu is d alpha for some potential alpha. Which is an n-2 form. So just for notation, the Lie algebra of exact divergence-free vector field. I'll denote like this. Where X alpha is the unique vector field that satisfies this condition. Right. So if M is compact, then there exists a nice Fréchet Lie group which has this Lie algebra as a Lie algebra. This is not obvious, but it's it here. So let me continue for the Lie algebra case. From the definition, you see that every such exact volume preserving vector field comes from a potential, right? So there's a map. There, and it's surjective by definition. Now the right-hand side is a Lie algebra, And we can put a bracket on the left-hand side as well. The derivative of beta along alpha.
Manifold is M, right? No.
Oh, it was M. Thank you. It's not so hard to see that this bracket makes omega n minus 2 into a Leibniz algebra. Not quite a Lie algebra because it's not skew symmetric. It's a left Leibniz algebra. And as Katrina said in the hour before this one, the nice way to write the Jacobi bracket in the context of non-skew symmetric brackets is this way. You consider taking the bracket with alpha as a derivation. So this is true, and if we put this Leibniz bracket on this topological vector space, then this map becomes a morphism of Leibniz algebras. Call this projection Br, and Br is a morphism of Leibniz algebras. Which means that if you first take the Leibniz bracket and then take the corresponding exact volume preserving vector field, that's the same as first taking the exact divergence-free vector field and taking the RD bracket. So this is just a one-line computation. You can do it yourself if you get bored in this. Well, maybe it's a nice computation to show that alpha beta plus beta alpha equal to something exact, but in general it's not equal to 0.
Exact n minus 2 forms. Does it become a Lie algebra?
Then it becomes a Lie algebra. Exactly. So let's denote that by omega bar. So this is a Lie algebra. And then, of course, this is a surjective morphism of Lie algebras, right? And if you think of a surjective morphism, then you might want to know what its kernel is. But the thing that takes alpha to the unique vector field such that IS of mu is equal to d alpha it's the cohomology. So x alpha is 0 if and only if alpha is exact, if d alpha is 0. But we only quotiented out, sorry, if alpha is closed. But we only quotiented out the exact part. So the kernel consists of closed n minus 2 forms modulo exact. The Rham cohomology in degree n minus 2. this is actually a central extension. So the reason is that if you're in there, then you get mapped to 0. And this Lie bracket was defined by taking the Lie derivative along x alpha. Right? So this is a central extension. And it's a central extension of Freccia Lie algebras because the kernel of this map is Great. And then I think you told us that the A in smart was for attributing honor to where it's due. So of course this is not my observation. This is a very simple thing to write down, and if you try to trace this back at some point, you get lost in the mists of time. So this is usually attributed and people probably have a reason for that, but then if you read the papers they refer to it, the statement is not in there. The earliest reference I could find was by Ismagilov, I think. And he actually studied not just this central extension of Lie algebras, but he also tried to find a central extension of Lie groups that kind of integrates this one. It's also rather prominent in a paper of Claude Roger. And Roger conjectures that this is the universal central extension of the Lie algebra of exact divergence-free vector fields. So I suppose what I want to talk about for most of this talk is that this is actually true. So this is joint work with Leonid Ryvkin and with Cornelia Vizman. Short version of the theorem is this is true. Slightly longer version is that if you consider this as an exact sequence of Freccia Lie algebras, then it's universal for central extensions of this Freccia Lie algebra by complete locally convex Lie algebras. So far, so good. Any questions?
We mean by universal.
Right. What do I mean by universal? So a central extension is universal if every other one factors through it. Right. So I have a Lie algebra G, then a map called universal if for any other central extension like this. So for the other central extension, say by R, I mean, you can put anything on the left-hand side, but it will not matter that much. For every other central extension, there exists a map which kind of intertwines with the identity here. and it restricts to a map. So in a sense, a universal central extension is universal if every other one comes from it. So any other central extension can be gotten from this one, and then by mapping out of it. So these central extensions, they correspond to two cocycles. That isomorphism classes of central extensions correspond to isomorphism classes of two cocycles on your Lie algebra. And the two cocycle is symmetric continuous bilinear map. Continuous because we want continuous central extensions, right? The important thing is that it satisfies some co-boundary condition. Take psi of x, commutator of y and z, and you cycle through, then you get 0. So if you have such a two cocycle, it's very easy to produce a central extension. Right? Just take the direct sum of your Lie algebra and R as vector spaces, and you twist the Lie bracket with the cocycle. On the right-hand side, for the Lie algebra, you have the old bracket. And on the left-hand side, you have the two cocycle. Okay, so from two cocycles, you get central extensions. And if those two cocycles are cohomologous, two cocycles are cohomologous if their difference is a co-boundary. And the co-boundary is some function of the bracket. From lambda, which is then automatically continuous. Then the central extensions are isomorphic. For suitable definition of isomorphism.
It could be larger than one dimension.
Come again?
You choose M correctly, then Hn minus 2 of M is larger than just
exactly.
one dimension.
Yeah. I agree. Yeah.
So you get the cocycle higher dimension.
Yeah, so there's two ways to phrase this, right? So one can say you have a cocycle with values in H2 of M, which is universal. You can also say every cocycle with values in R comes from a linear map out of this center into R. So that's the question of, do you want one cocycle to rule them all, or do you want to classify the different ones? So here, the one cocycle to rule them all picture is nice, because this Lie algebra is perfect. Otherwise, it's better to list them one by one. I'll take the second one. So I'll take the point of view that our problem is to classify all these cocycles modulo this notion of isomorphism or boundaries.
Sorry, I have a question related to Peter's question. Like, as solver physicist, I see this exact sequence like exact component of my vector field plus harmonic component of my vector field give me a divergence-free vector field. In that case, like this gives me kind of like 0 h1 of m and omega 1 divided by d omega 0 and x ex. In that case, like I have like solve h1, but like, and I got like omega 1 divided by omega 0. Doesn't this give me also a central extension, or like, don't I get a central extension by this?
Sorry, if you do for divergence-free vector fields in, or if M has dimension 2, is that?
Yeah, okay. Long and short, do I also get a central extension if I have like 0, h1 of m, omega bar 1, x ex 0.
Would be the map from omega bar 1 to x here? What would be the map from omega 1 bar to the exact divergence-free vector fields?
I just take an exact component of my vector field. Like I just remove the harmonic component of my vector field. That's the map.
Is that a Lie algebra morphism? Maybe we should talk about this.
Yeah.
But connected to your question, I would like to make one remark. I was a bit short. Right, so this is true if the dimension of your manifold is at least 3. Dimension 1 is not so interesting. Dimension 2 is interesting, but then exact divergence free is the same as Hamiltonian, and then the statement as it is there. Another statement is true. Right. I don't want to give the full proof of this theorem, but I want to give a bit of intuition about the outline of this proof. So, so the strategy is that what you would like to prove is that these two co-cycles are differential operators. And then the obvious problem here is that this Lie algebra of exact divergence-free vector fields is not a C-infinity module. And neither is the thing in the center. Neither is this one. And if something is not a C-infinity module, it's not so clear what a differential operator should be. So the solution is kind of already on the blackboard. You look at the Leibniz algebra, right? All potentials. This is a Leibniz algebra and also a C-infinity module. And because it's a C-infinity module, it makes sense to ask whether or not something is a differential operator. So this is the trick. For these Leibniz algebras, there's a well-developed kind of theory of Leibniz cohomology by Leonid, Ryvkin, and others. And using this observation that this omega bar really comes from an omega, which is a Leibniz algebra, you can kind of tap into that circle of ideas. And that allows you to kind of work with differential operators, and then you can work order by order, and then life gets maybe not easier, but you can solve the problem. Let me outline a little bit what happens. So the basic lemma here is that that this thing is not just a Leibniz algebra; it's a perfect Leibniz algebra. Here I don't just mean topologically perfect, I really mean perfect. So every element can be written as a finite sum of commutators. Another observation is that we already established that, that alpha beta plus beta alpha is exact. Right? The converse is also true. So every exact n-2 form can be written as a finite sum of alpha beta plus beta alpha. In other words, the ideal of squares in this left Leibniz algebra coincides with the exact forms. This is not obvious, but it's a thing. So what do you do then? Let's say this is one. What you do if you have a 2 co-cycle, you're trying to kind of establish what all the 2 co-cycles are. First, you put it back to this Leibniz algebra. And you can identify that with a map from omega n-2 of m, the continuous dual of that one. And actually, you want to do this at the compactly supported level. So if your original map psi was a 2 co-cycle, then this guy will be a 2 co-cycle in this Leibniz cohomology. And then this one will be a 1 co-cycle with values in the continuous coadjoint representation. Now you use this perfectness of the Leibniz algebra to show that this is actually a local map, support decreasing. And if a linear map from, say, compactly supported functions to distributions decreases the support, then by Petrus' theorem, it's a differential operator. And then you're in business. So then you can try to kind of classify these things. Using the fact that they're differential operators, you can show that all of them are trivial in this Leibniz cohomology. And that's not obvious, that's a rather lengthy calculation. But you can imagine that if you know that something is a differential operator, you can kind of work order by order, and then you can get through this.
To the Schwarz-Kerner theorem, the Schwarz-Kerner theorem, of course, you see differential operators of.
Yeah, so that's also kind of a massive ingredient in Petrus' theorem. But you want to be on the diagonal. That's where you really use this perfectness. For medium the algebras, you just have bilinear maps. Okay, so you know that they're differential operators. Then you can show that in this Leibniz cohomology, they're trivial. Fact. But you want to go back to this original Lie algebra. And there you need this ideal of squares. Second idea here is that you use 2. You can prove that if this one is exact, so if this one is exact on And using the fact that this one is d of omega n minus 2 is the ideal of squares, you can prove that psi itself factors through omega bar. So there's one version of this for omega, then there's also a version of this for compactly supported forms, and actually the compactly supported part is harder to prove, and it implies the non-compactly supported part, because this Fréchet topology is somehow very coarse, I think. Any questions about this?
Potential of per star psi, or?
I should first use differently. It's d of something, and the something factors through omega bar. Any other questions?
Where do you need m to be compact in?
I don't. So for this, we're on the Lie algebra case. Non-compact is perfectly fine. Any other questions?
Can you repeat again why compactly supported case is more difficult?
Well, somehow because in the Fréchet topology on the non-compactly supported ones, the compactly supported ones are dense. Somehow, if you know what happens on the compactly supported vector fields, you know that your 2 co-cycle is continuous, and it determines what happens everywhere. So if you prove the compactly supported part, then that kind of implies result for the non-compactly supported part, why this continuity is there. Any more questions?
Do you have a formula?
Yes. Very simple. I should have mentioned. The universal co-cycle from values in the cohomology is just taking plugging both of them in the volume form, you get an n-2 form, and you take the class. This is essentially the only one.
X n-2 form x I mu closed in general. So you might take a projection to the closed 2 forms so that you can take the class that the Rham
It's kind of on your co-authors to ask the hard questions.
It's a continuous projection.
If you still project.
If you take d of this, you are very near to the derivative. The Lie derivative goes through D.
Derivative is just contracting with the bracket x. Contracting mu with the bracket of zero.
Okay, we should. Certain about the statement, right? to get the co-cycle, you probably split this. The splitting should have to do with your projection, I think. And this projection is not really canonical, right? So no general formula. There exists one, but not a canonical one.
Sequence is split. So there is a section.
So it's linearly split. It's linearly split. So the splitting is not a Lie algebra homomorphism. The failure to be a Lie algebra homomorphism is the co-cycle. So somehow there's a general formula that
Should be linearly and continuously split.
it is linearly and continuously. Yes. And that's not trivial, but it's true. Right, so you choose a continuous splitting. So for every exact volume preserving vector field, you choose a potential. But just like in the symplectic case, Hamilton functions for Hamiltonian vector field are not unique. And the failure for this thing to be a commutator bracket is something like whether the action is Hamiltonian. So a similar thing is here. So you choose potentials, and then you see whether or not this map sigma is a Lie algebra homomorphism. And it's not. And the failure is kind of this curvature expression that gives you a co-cycle. If you choose a different splitting, you will get a different co-cycle, which is cohomologous. And if you choose any one of those, then the statement is that any other two co-cycle kind of factors through this.
Make a bar. The continuous linear splitting exists if and only if the cohomology has a direct summand, a complement,
Yes.
a closed complement.
Yes.
Why is this the case? I mean, couldn't you construct a manifold where Hn minus 2 of M is infinity dimensional if it has countably many holes or so?
I found a statement in the literature that this works, paper by I think. I do not at the moment remember the proof from start to finish, but this was a bit of work. So there is linear and continuous splittings, but I think one needs to work to prove this.
No, of course you have manifolds with H2 or something.
Of course.
Countable, at least countable dimension.
Of course.
Yeah, so I think for those it works well. Certainly in the compactly supported case. Okay, but either way, you see why I prefer to work with the Lie algebra extension rather than with the universal cosine.
You said Ismagilov found the group co-cycle. Does he have a formula?
I was not able to understand this paper from start to finish. So there's two different things, right? So you can either kind of integrate to a group to co-cycle, or you can integrate the central extension to a group extension. I think the second point of view is what you want to do. This is what he says he does, and he has construction which I don't quite understand. I will say some words about it. I have a little time to say a few words about it.
So one problem is, okay, now we have a universal Lie algebra extension. Maybe we would like to have a universal Lie group extension. Talk about Lie groups, I will be assuming that the manifold is compact. Right? So now on M is compact and connected. And then the strategy is somehow to use the action of this exact volume preserving diffeomorphism group on the nonlinear Grassmannian codimension to embedded submanifolds. There exists connected spatial Lie group of exact volume preserving diffeomorphisms. It acts on the codimension to Grassmannian. It's also a nice smooth manifold, and it has a symplectic structure. Sometimes called the Marston-Weinstein symplectic form. So what it does is the following. Symplectic form is a skew-symmetric bilinear form on the tangent bundle. Right? If you look at the tangent space of the Grassmannian at a certain submanifold, same as the sections of the normal bundle. Right? Corresponding picture would be that if the blackboard is your manifold, say my blackboard is three-dimensional, then a codimension one submanifold is a one-dimensional curve. And then if I want to say what a tangent vector is, I want to say what happens if my curve moves a little bit. And that's the same as specifying a normal vector field. So what does this symplectic form do? Plug in two vector fields, and the output is what you get if you take these two vector fields, plug them into the volume form. And then integrate the result over the submanifold sigma. So claim is that this is a symplectic form. Another claim is that this action on the Grassmannian is Hamiltonian, but it's weakly Hamiltonian.
Grassmannian. Oriented submanifolds.
Yes. Yeah. Yes. Thank you.
Here's an observation. If you take this action of the exact volume preserving diffeomorphism group, differentiate it, you get fundamental vector fields. Right? So every vector field on your manifold, which is exact and divergence-free, it gives you a vector field on the Grassmannian. That is to say, at every point, it gives you a tangent vector. That is to say, at every submanifold, it gives you a section of the normal bundle. Now, guess what that section would be? So x sub sigma is the fundamental vector field at the point sigma. That's just what you get if you take the vector field on your manifold M, restrict it to sigma, and take its class, which is a section of the normal bundle. So if you use this, then you see that this co-cycle that I would get from sigma, if I consider sigma as a linear map from my cohomology to the real numbers by integrating over it, that is just symplectic form applied to the fundamental vector field. Also, this action is not just symplectic, it's Hamiltonian, but it's weakly Hamiltonian. Meaning there do not exist equivariant moment maps. So one possible strategy for getting central group extensions.
Why your psi is not closed? Because if this psi that you wrote IV, IW of mu would be closed. Sorry. See, it's not exact. Yeah.
I will close quickly.
And outline the strategy of what one would do. So what one wants to do is choose a pre-quantum line bundle over your Grassmannian. You have an action downstairs by the exact volume preserving diffeomorphisms. And then you want to look at the automorphisms of the pre-quantum line bundle, which cover this action downstairs. Now for every connected component, this gives you kind of one extra degree of freedom, right? You specify what connection preserving diffeomorphism.
Automorphisms which preserve a connection one form.
Exactly.
Because otherwise it's
The
much bigger.
automorphisms of the line bundle with connection.
Yeah, otherwise it's not an
The
S1
pre-quantum
extension.
cover. Exactly.
And even this one is problematic because there are very many connected components in this Grassmannian, right?
As many as there are nodes.
Take one.
Yes, so what you can do is you can take one, and then you
get a one-dimensional central extension. And that works well. So there are various sources of pre-quantum line bundles. One is using homology. So Van Haller and Cornelia, they use this. Another way to get these pre-quantum line bundles is using differential characters. Going to work with Tobias Diez, Karl-Hermann Neeb, Cornelia Vizman. And here's the nice thing. In 3 dimensions, there is one more way to get these pre-quantum line bundles, and that's by using bundle gerbs with connection. So you choose a bundle gerb with connections whose curvature is your volume form. Because if you're in 3 dimensions, then your volume form is a 3 form, and integral 3 forms are curvatures of some bundle gerb. Then there is a procedure called transgression, and it turns these bundle gerbs into line bundles over loop space, like a Grassmannian with some extra freedom. And there you can do this trick. And here's the nice thing. If you start with a bundle gerb and you get a line bundle, then you get a line bundle with connection, but you get some extra structure. It's called a fusion structure. And the fusion structure is a piece of data which kind of connects the different connected components of your loop space. And that solves the problem that you kind of have to restrict to one connected component. That's the reason why in dimension 3 we can find group extensions by H1 of M with values in U1. But in dimension bigger than 3, we can only kind of integrate these co-cycles which take values in the real numbers. Thank you for your attention.